Hi, welcome to this section of the Advanced Calculus 2 Tutor. And in this class, we're going to continue our study of Advanced Calculus, Calculus 2, and we're going to cover some topics in Calculus 2 that are very important and things that typically trip up a lot of students. We're going to cover a lot of material, and some of it is going to be a little bit disjointed from one topic to the next because that's the way Calculus 2 is there toward the end. You study one topic, and then you'll go off and you'll study another topic. It may not have much to do with the topic you studied right before, but we'll do that because that's how the textbooks usually go. But everything in this class is very important to continue on into Calculus 3 and also into differential equations and all your topics in advanced engineering and math and things like that. So this section is going to start out with the inverse trigonometric functions. Now you all know what an inverse trig function is, I think, okay? And we'll talk about it here in case you don't. But in this section, we're going to focus on inverse trig functions and how they kind of apply to calculus. This is an introductory section explaining what the arc sine and the inverse sine and the inverse cosine and things like that are. But we're doing it from the point of view of what we will be using it for later, which will be your calculus. When you're doing your integrals and your derivatives, you're going to need to know this stuff by the back of your hand. So I'm kind of putting this up front. There's not that much calculus in this section, but it is essential baseline material that you'll need to know. Okay, so first let's talk about our favorite trig function everybody knows and loves, and that's called the sine, okay, the sinusoid. So I'm going to draw it up here on the board, and we're going to review a few things because that's what this section's about. Okay, so you have your graph, okay, that we've all know and love, okay, and here will be x, and here will be sine of x. Okay, so here x is just an angle, okay, it's an angle in radians, pi over 2, 2 pi over 2, 3 pi over 2, whatever, and when you put this angle into the sine function, out spits a number, and if you recall, the sine function always spits out a number between -1 and +1. And by the way, a lot of the stuff that we're talking about in this section, I'm covering it from a calculus point of view, which you'll need to know. But if you think you need a little more help on the basics of some of the things we'll talk about, the unit circle and taking your inverse trig functions and such, go off and take a look at the trig and pre-cal tutor. I know you guys are off in Cal 2 now, that's why you're looking at this course, so you probably know that, but everybody needs review every now and again, and so that's a really good class to review the unit circle and your radians and how to take your sines and your cosines and your cosecants and things like that. So let's continue on. What we have here, I'm going to switch colors here. This is something you probably should already know. You have pi over 2, okay, pi, 3 pi over 2, and 2 pi. Okay, so one full circle, because 2 pi radians is a full circle if you recall. And on this side, we have negative pi over 2, and we have negative pi, and we have negative 3 pi over 2. And I'm going to go ahead and extend this over here, and we have negative 2 pi. Okay, so what we have here is, okay, and I'm going to draw a little circle here because I'm going to reference this circle as we talk about this. This is just a unit circle, okay? Nothing special about this, okay? So just to refresh your memory, because everybody needs a little refresher, okay? This guy, this is what we call 0 radians. As you trace around this circle, you'll eventually hit pi over 2 radians, okay? And then 2 pi over 2 radians, which reduces to pi, because 2 pi over 2 is pi. So 0, pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. And 4 pi over 2, you've completed one circle. 4 pi over 2 is just 2 pi. So as we go here, we're just taking this graph and we're kind of unfolding it into a kind of a linear fashion. So here you start at 0, you got your 2 pi over 2, your pi over 2, your 2 pi over 2 reduces to pi, 3 pi over 2, 4 pi over 2 reduces to 2 pi. So what you have here is you've got your angles stretched out here, and then you got your corresponding negative angles here. Okay, so switching colors again because I'm color happy in this section. Your sine function, recall, looks like this. It goes from +1 to -1. That's the envelope. Okay, and it starts out here, and it makes goes up there to the top, goes down here, and it goes up here. Okay, and then it continues in negative. It goes like this, on through pi, like this. So that's your favorite sine function you all know and love, okay? You start out at 0, you reach a peak at pi over 2, because as you increase the angles up to pi over 2, the sine, which is, by the way, don't forget, the sine function is the projection of this circle onto the y-axis, which I haven't labeled here, but that's the y-axis, okay? So as you take the circle and as you go up like this, the sine function is just looking at the projection of this thing on the y-axis, okay? So when you're here at 0 radians, the sine is 0 because there's no projection on the y-axis down here. So that's why it's 0. As you make your way over to pi over 2 radians, okay, the projection all lies along the y-axis, so it's equal to 1. And as you go around, you'll see it kind of make this shape, because as you turn around the circle, the projection along the y-axis changes. So that's all review, but I want to put it on the board because what you'll see here in a minute is pretty important. So here you have your sine function that you've studied for a long time and used in Cal 1 and Trig and other classes. Okay. Now what I want to call to your attention is, okay, just sort of the obvious. We all know that if you take the sine of an angle, what you get back out of that operation is a number. Okay? Now, we all know that this number lies between positive 1 and minus 1, because any angle that we put in, no matter if we go on to infinity or negative infinity, any angle we put in is going to go into this function we call the sine function, and it's going to spit out a number that's always going to be between this. So there's repetition here. You have one cycle of the sine function, and if you keep going, you'll get another cycle and another cycle and another cycle. No matter what angle you put in, you always get something between positive and minus 1. Okay? So you'll find that it's very useful, and something you'll have to learn, to define something called the inverse sine, or the arc sine. So you can define the opposite of the sine function as the arc sine, okay? The arc sine of some number, meaning this number here, I'm trying to draw an analogy here, is going to equal an angle. So it's an opposite, you see. The arc sine, the inverse sine, and by the way, by analogy, the inverse cosine, the inverse tangent, the inverse cotangent, all of these things, all of these trig functions, you know, they all have an inverse. They're basically an opposite, okay? And they all take a number, okay, which by the way must be between positive and negative 1, and they will map it and return back an angle to you. Okay, so it's exactly the opposite. Sine of an angle gives me a number between negative 1 and positive 1, and arc sine of some number between negative 1 and positive 1 gives me back some angle. If I try to put a number in here bigger than positive or minus 1, it's invalid, it doesn't work. If you put that in your calculator, arc sine of 34, you're going to get an error, because this function is only defined between negative and positive 1. So it doesn't make sense to put a number bigger than that in there. It just doesn't work. Okay? So making this a little bit more formal, instead of having the word number around there, what you really have is the arc sine of some number x. Okay? We also call it, you also see it like sine with a negative 1 up here of x. These are called the inverse functions, okay? And this negative 1, by the way, this is not an exponent. This is not raised to a power. This is back in your algebra when you talked about function inverses. This negative 1 up here in the exponent means it's an inverse. So this arc sine, which is the same thing as this, it's just written differently, different notation, it is an inverse, literally the inverse of the sine function, okay? So there's something very, very important I want to point out to you here. Now that we've looked at this a little bit, you might want to burn this in your head, okay, just to kind of keep it in your head. But notice the following. If I take the arc sine of 1, which, by the way, this is 1, so remember, I'm taking a number along this axis, I'm popping it into this arc sine function, and I'm going to get an angle back. One single angle is what I'm going to get. If I take this and I put it in my calculator, or you just look at the graph here, you can see the angle you're going to get back is pi over 2. Okay? So if I put an arc sine of positive 1, I'm going to get back an angle, the corresponding angle, which is pi over 2. Okay? That's what that's telling me. Okay? But also notice that if I put in the arc sine of 1, notice that an equally valid angle is negative 3 pi over 2. Because look, if I go over here and map it over here, negative 3 pi over 2 is an equally valid angle. And likewise, if I do the arcsine of 1, I can also get back 5 pi over 2. Okay? And you can see that if you just go ahead and take this onto its logical conclusion, you know, pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, it ends up back up here, way over on this side. That's also corresponds to the value of 1. So you see what's happened here. We have a dilemma because a function, right, or some relation that we're going to be used here and useful in calculus, it's not very useful if you put the same number in and you get different values out. I mean, how would you program a computer to do that? Okay? I mean, literally, look at what we have here. We've taken a number 1, we've put it in our function, and we've shown via the graph that multiple values are valid, okay, as a result of that. So how would you program a computer to do that? What value do you pick? Okay, the answer is you can't really program a computer to do that. So if you put your calculator and you take the arcsine of 1, you will not get 3 values back. You will only get 1 back. You will only get this one, pi over 2. Okay, so you can see here by looking at it that multiple values are valid when you take the arcsine. So what we have to do in calculus and what is done to kind of remove this ambiguity of what's the proper value to return, what we do in calculus is we just look at a certain part of this graph. Okay, so what we will do then is we will then look only at this part of the graph. Let me just draw a little circle kind of around it. Okay, and then the way you do it is you say, okay, look, we know the sine function goes on forever and ever. Okay, we know this. And we know that if we put a 1, if we look at the arcsine of anything up here, we know there's going to be multiple values spaced equally apart that is a valid angle that would satisfy that. But we also know that that's not very useful to have infinite answers to a problem. So what we're going to do when we define the arcsine function is we're going to define it only to return values in a certain range. And we're going to constrict that range to be right here. Okay? So you see, if you put negative 1 into the arcsine function, you would get negative pi over 2. Okay? You'll never get anything over here because we're going to define the arcsine function only to return values from negative pi over 2 to positive pi over 2. So any number you put in along this axis and take the arcsine of it, you will get values upon this curve corresponding to angles, okay? But you will never get anything over here and you will never get anything over here. And that is just simply a definition. It's nothing magical about it. It's just that the mathematicians that invented the arcsine function realized this, and they said, well, we can't have it returning a ton of different answers. We're going to constrict it to look in a certain range, and we're going to define it to only return values in this range. Okay? So, I don't think I need to write that down, but that is what we're doing. We're going to restrict it to do that. All right? So, for instance, okay, just as a for instance, and I'm going to write a whole table over here to give you some help on all of the different trig functions. Okay, so for instance, arcsine of x is equal to y. This is the definition of the arcsine function. When you take the arcsine, you're taking the arcsine of a number between negative 1 and positive 1, and you're getting back an angle. And what you'll see in the book is it returns values of y that's negative pi over 2 to positive pi over 2. Remember how to read this. Y is greater, reading it this way, greater than negative pi over 2, and y is less than positive pi over 2. So what this just simply means is if you have negative pi over 2 here, and if you have positive pi over 2 here, it's greater than negative pi over 2, so it's over here, and it's less than positive pi over 2. So basically, it only returns values in between here, which is just what we said. We're looking at that region of the graph between these points, and that's all it's going to ever return. So, for the arcsine, we have shown with an example and talking through it that it's only going to be defined to return values in this range. And it turns out that all of the trigonometric functions are really in this boat because all of them are cyclic. Okay, all of them are cyclic, and you're going to run into the same problems with multiplicity on all of them. So next, what I'm going to do, without a detailed proof of every one of them, I'm going to write down the table that you'll see in your book of what all the trig functions return in the ranges, and now you'll know at least why. You still have to memorize the ranges. There's no way around that. You have to memorize them, but at least you'll know why they exist, instead of just being this mysterious thing. Okay, so here is a table of the inverse trig functions and the corresponding angles that they're going to return. So we've already talked about the inverse sine function. It takes a number in and it spits out an angle, and it returns an angle between negative pi over 2 and pi over 2 inclusive. And remember, these are just definitions. These are things that the brilliant math guys before us defined to make these functions easy to use in calculus when you're taking derivatives and integrals. So these ranges here are just a range of angles, like we talked about before with the sine, so that we can be guaranteed to get one single angle back given an input. Instead of getting a multiplicity of angles back, you have to cut it off somewhere. So this is the ranges that they've chosen, and it makes the math simpler as we go on by having these ranges. So the inverse cosine, if you take the inverse cosine of a number and you get an angle between 0 and pi inclusive. Okay, and it's a different range than you have with the sine function, but it's different because the cosine function is different. The cosine function is a shifted version of the sine function, and so the range of angles that it's going to return, we could pick any range over a period, a certain period of that cosine function, as long as we got a one-to-one angle back. But this range is one that was chosen as the accepted standard, and just something you're going to have to memorize, and it makes the math easier when you're talking about the inverse cosine function and the derivatives later on. Tangent, when you take the inverse tangent of an angle and you get a number and you get an angle back, it's going to return from negative pi over 2 to pi over 2. But notice that it's not inclusive. It's not going to actually return negative pi over 2 and positive pi over 2 because we don't have these little equal signs underneath the inequalities here. And the reason it doesn't return those is because if you look at the tangent function and you were to graph the tangent function, you'll see some singularities, some asymptotes, vertical asymptotes there. And so you obviously can't define it to return angles that cross a vertical asymptote, like would happen at negative and positive pi over 2. So you just define the function to not return those values and only return the values between them. Okay? Inverse cotangent, getting down into the lesser used functions, inverse cotangent is going to return an angle between 0 and pi, not inclusive. And if you were to graph this cotangent function, you would find singularities, and this range is chosen so as to never return an angle that crosses one of those singularity boundaries. That's why it's done that way. And same thing for secant and cosecant. The inverse secant function returns an angle between 0 and pi over 2, and also between, or I should say, pi and 3 pi over 2, and it was chosen that way because if you graph the secant function, you'll see some singularities. So if you look at this range and this range compared to the secant graph, you'll see that these ranges of angles cover a complete path along the secant function without crossing one of those asymptotes. Because when you define it, you want to define it to return angles to you, and you don't want it to cross any boundary where you have any kind of thing that goes off to infinity. So that's why the secant and the cosecant functions are split up like this with different ranges, because you have some asymptotes that fall in there, and we're choosing the ranges so that you never return an asymptote. So those are the inverse trig functions and the corresponding range of angles that they return. One thing I just want to point out to you here is you're going to have to memorize these things. I know it's a pain, but you're going to have to do that, and that's why I put it here. You're going to need it in your problems, and you're going to need it on your tests. If I had to focus on some, I'd focus on these because you'll probably have fewer problems dealing with these, but certainly you'll need to know all of them. But if I had to focus, I'd focus on the first three here because those are more used, and the other ones are not. One final thing I want to say, the secant and the cosecant, these range of angles here, remember these are just arbitrarily chosen by the math guys so as to give us a function that returns one angle back for an input. That's what we talked about before. You can choose different ranges to do that, okay? Most of the books, almost all of them, are going to use this accepted range of values as the definition of the inverse secant and the cosecant functions. Not all of them do. It doesn't mean that your book is wrong. It just means that they chose a different standard. Now these guys were chosen here by most textbook that you'll find because later on when we define the derivative of these functions, this definition here of the angles makes these derivatives simpler. So when you're doing your complicated derivatives and your integrals, it's going to make life a little bit easier. Okay, now what we're going to do now that we've talked about the inverse trig functions and the angles that they produce when you pop a number into the function, you get an angle back, and we've talked about the different ranges of numbers that you'll get back and angles for the different trig functions, we're going to work a few problems. They're going to be rapid fire, really short and sweet, simple little problems to kind of illustrate what we're talking about. Okay, so let's just go right to it. The first one is going to be, what if you were given, find the, let me go ahead and switch colors here. Find the inverse cosine, or the arc cosine, of -1. What is that going to equal? Okay. Well, the first thing you need to do, anytime you have the inverse of a trig function of a number, what I always do every single time I do it is, this is going to return some angle, right? And what you need to do is you need to always rewrite it. This is what I always do. I always say, well, what this is telling me, what this is asking me is the cosine of some angle, which is what would have been here, okay, is going to equal -1. That's what this is telling me. So if you have the inverse cosine of a number returning an angle, that means that you're trying to find cosine of some angle that I do not know what this is going to give me -1. And on top of that, we've already talked about the fact that these inverse cosines can only return angles in a certain range. So if you look back or rewind the tape over to the previous part, you'll find that the angle there for cosine is going to always be between 0 and pi. Okay, so whatever angle you get has to be between 0 and pi, and that's going to be the angle that will give you the cosine of -1. So I think you can probably convince yourself, because I chose a simple problem on purpose, that the angle here that you're going to get is going to just be pi. Okay, is going to just be pi. And the reason it's going to be pi is if you just go back and look at your unit circle, right, that we've all come to know and love, this is, this is 0 radians. Okay, this is pi over 2 radians, and this is 2 pi over 2 radians. Okay, 2 pi over 2 reduces to pi, right? So over here at pi radians, okay, if I take the cosine of pi radians over here, and cosine is the projection of whatever line, my little line here that I'm moving around onto the x-axis, okay, then it's going to be projected over here to -1. Because this is +1 and this is -1. So as I move my unit circle radius over here and get over to pi radians, okay, the projection to the x-axis is going to be -1. So that's why I said that the answer, the angle has to be pi. Okay, if I just chose it over here, then that would give me +1. Cosine of 0 or cosine of 2 pi is +1. Well, that's not what we had. We had to make it equal to -1. So we knew we had to be over on this axis, and that's pi radians. Now, the thing you always have to do when you get an answer is you have to say, okay, I found an angle so that if I take the cosine of this angle, it gives me -1. But is this angle in the range of the angles that the math guy said that we defined? And the answer is yes. Pi falls between 0 and pi inclusive, because this inclusive sign here. So we're done. That's the answer to that question. We don't have to do anything more than that. Okay, move on to another one. We'll get some practice. What if we had the inverse tangent of square root of 3? And you wanted to find what angle this thing returned. So we're putting in a number into the inverse tangent function, and we have to get an angle out. Okay, and this angle is going to be the angle that we're going to want. Now, what this means is that the tangent, just rewriting it, the tangent of some number, some angle, is going to equal to square root of 3. That's what this means. I'm just rewriting it. Tangent of some angle is going to give me that. That's what I'm doing. So I need to start walking around the unit circle, okay, to find an angle so that when I take the tangent of it, it's going to give me square root of 3. But remember, anytime you have a tangent, you really just need to start thinking in terms of sine over cosine. That's what I do, okay? Every single time I do this, I always have to do this. But I have to start looking at angles. I start putting in angles here and taking the sine and the cosine and seeing which angles are going to give me, is there an angle that's going to give me square root of 3. Okay? Now, one more thing you just always need to keep in mind, that for the tangent function, okay, the angle that's going to be sent back to us has got to fall between -pi over 2 and pi over 2. Okay? I guess I should write this in terms of theta. It really doesn't matter. Whatever label you put here, y or theta or whatever it is, it's just saying that whatever number you get as a result of this operation, inverse tangent on a number giving you theta, has got to be between -pi over 2 and pi over 2. So let's see if we can find that number. Okay, I'll go ahead and switch colors here. If theta is equal to pi over 3, let's see what happens. Because you're going to find that when you do these, what you're going to end up doing is, it takes practice like anything else. What you're going to do is you're going to start at some angles and start walking around until you find one that works. And then eventually you'll get so good at it you can just think of them. But let's start over at pi over 3 and let's see what happens. If I choose pi over 3 as my angle, then what happens if I take the sine and the cosine? I have sine of pi over 3, and I'll have cosine of pi over 3. And what is this going to equal? Well, the sine of pi over 3 is like the sine of 60 degrees, so that's the square root of 3 over 2. And the cosine of pi over 3 is just the same thing as the cosine of 60 degrees, which is 1/2. Okay? And so you have square root of 3 over 2 over 1/2, and these 2's can just cancel with each other because they're both in the denominator. So what you're going to have here is the square root of 3. So we got the right answer. Okay? So never forget the forest for the trees. Don't forget that the answer we got, which was pi over 3 in this case, does fall between the range of negative pi over 2 and pi over 2. So that is correct. Okay? That is okay. We took a number, we plugged it into the inverse tangent function, and we got an angle back that fell between the range we needed to find as prescribed by the table there. Okay? The way we did it is just by working backwards. You just find an angle so that when you plug it into the tangent function, which the tangent function is the sine over the cosine function, you find an angle to give you the answer you want. I mean, you may have started off with something else like pi over 4 or pi over 6, and you would have gotten the wrong answer. You would have worked your way around to the proper answer. That's what you have to do. So if you look at some of these things and you're like, man, it's not hitting me, just start with an angle and you'll get good at your trig functions. You have to know those by the back of your hand. Okay, the next problem is going to be find the inverse cosecant of square root of 2. Okay, that's what the problem would say. Find the inverse cosecant of square root of 2, and that's what you have to do. First thing you need to do is rewrite it. That's what I do, and that means that this is going to return an angle. The cosecant of some angle is going to equal square root of 2, and it's up to us to find what that angle is. So when I'm presented with a problem like this, when I have cosecant or secant or cotangent or something like this, the first thing I do is I rewrite it in terms of sine or cosine. And so if you don't know the trick there, I would suggest you learn it. You just write the trig functions in order: sine, cosine, tangent, cotangent, secant, cosecant. Just memorize this ordering, and then it's really easy because cotangent is 1 over tangent, secant is 1 over cosine, cosecant is 1 over sine. So they kind of form a rainbow like that. So what I do is I say 1 over the sine of an angle is equal to the square root of 2. Okay, that's what you're doing here. You're taking the cosecant, you're rewriting it in terms of sine, because personally I'm more confident and comfortable and familiar with working with sine, cosine, and tangent. So I always rewrite my cosecants, secants, cotangents in terms of the other trig functions when I can do it. So I have 1 over sine of theta, and in order to get this in a form that I'm more comfortable with, I'll just flip both of these fractions over. So I'll say sine of theta is equal to 1 over square root of 2. So I just divide both sides, 1 over both sides, and just basically divide both sides there, take the reciprocal, and so you have this. Now I've got the problem out in a form that's much easier. Sine of an angle is 1/2, and don't forget here that now that we're talking about a sine function, the angle that can be returned from a sine function is negative pi over 2 to pi over 2, inclusive. Okay? So all I got to do now is work my way around the unit circle, find an angle that does this, and that angle needs to fall between this range. Okay? So what I'm going to do is I'm going to say, first I'm going to draw a little unit circle here because it's always a good reference to have. Okay? And I'm going to say, well, what if, let's say, what if theta is equal to pi over 4? What happens if theta is equal to pi over 4? Well, then what will happen is I'll have sine of pi over 4, okay? Pi over 4 is here at 45 degrees, and sine of pi over 4, you should know, is square root of 2 over 2. Okay? So at first you might look at that and you might say, well, that isn't right, because I was supposed to find an angle, so I took the sine of it, I get 1 over square root of 2, and this returns square root of 2 over 2. Okay? But looky here. I can actually take this, just to prove it to you, these are actually the same thing. I can take this fraction and multiply it by square root of 2 over square root of 2. I'm just multiplying by 1. Square root of 2 over square root of 2 is just 1. And so if I do the simplification on the top, I'm going to have square root of 4 2 times 2 is 4. And on the bottom, I'm going to have 2 times the square root of 2. Okay? So on the top, square root of 4 is 2. And on the bottom is 2 times the square root of 2. And you can see right here the 2's cancel. So you have 1 over square root of 2. So it turns out that pi over 4 was the correct angle. Okay? And pi over 4 does fall between the range of angles that inverse sine function is legally able to return. Okay? If I would have picked an angle, obviously I don't want to pick an angle outside of this range because that isn't illegal. Okay? It has to return an angle there. So you start with the cosecant. We turned it into 1 over a cosine, and then we just flipped both sides over so that we were dealing with sine of an angle equal 1 over square root of 2, and then you just kind of work your way around the circle. You would find quickly that if you pick other angles, you're not going to get the right answer. Okay? Square root of pi over 4 here, we take the sine of it, we got square root of 2 over 2, and we showed by this multiplication exercise here, multiplying by root 2 over root 2, that it actually is the same thing as what the problem gave you. Okay? Okay, the next problem says cotangent inverse of negative square root of 3. So I'm taking the inverse cotangent, or the arc cotangent, of negative square root of 3. All right, and the way I always proceed next is I rewrite it. I say the cotangent of some angle, because remember this is going to return some angle back. Cotangent of some angle is just equal to negative square root of 3. Okay, and that's what I want to do. And the next thing I do is I like to, when I'm dealing with cotangents, secants, or cosecants, I always like to rewrite them. Cotangent is just simply equal to cosine of theta over sine theta. Okay? That's what this is equal to. The reason it's equal to that is because the tangent function is sine over cosine. And if you remember back to the rainbow, I already showed you that cotangent is equal to 1 over tangent. So what you have here is 1 over sine over cosine. So you have cosine over sine. So really, to boil it down to you here, just something easy for you to remember. The tangent function is sine over cosine. The cotangent function is cosine over sine. That's really the thing you need to remember. Okay? So we wrote the cotangent function as cotangent over sine. And the reason I'm doing this is because personally I just like to work. I like to work with these cotangents kind of split up because I know how to deal with cosines and I know how to deal with sines. It's much easier for me to figure out the answer if I'm looking at these fundamental functions. Okay? So I've got cosine over sine is equal to that. And just to make life even a little bit easier, I'm going to divide both sides, take the reciprocal of both sides. So I'm going to say sine of an angle over cosine of an angle is equal to negative 1 over root 3. It's just a personal preference. You don't have to do that. You could have started here and gone around the unit circle and done it, but I prefer to do it this way. I prefer to have sine over cosine like this. Okay? And you can do that because I took the reciprocal of both sides. 1 divided by this, 1 divided by this. And that's a legal thing to do as long as you're doing it to both sides. So now what you want to do is you want to look at your unit circle, okay? And you want to start moving around the unit circle starting at 0 and kind of picking intermediate values. And you want to just basically play with it until you start getting an angle that's going to give you the right answer here. And that's all you really have to do. Okay, so what I want to do first is I want to say, what if the angle I pick is 5 pi over 6? Remember, pi over 6 is like 30 degrees, so that would be around like here. This is pi over 6, 2 pi over 6, 3 pi over 6, giving you pi over 2, 4 pi over 6, 5 pi over 6. So 5 pi over 6 is something like this, okay? This is 5 pi over 6, okay? I know it pretty much has to be in this quadrant because I have a negative here, and so, you know, I need to have some way to get a negative value, and here my sine is going to give me negative. I'm sorry, my cosine is going to give me negative, and my sine is going to give me positive, so that's going to help me out, okay? But if that doesn't make sense, I mean, really and truly all you're doing is picking values until you find the right one. So if you don't know or have an instinct, you just kind of start doing that. So what happens if we do that? We take the sine of 5 pi over 6 over the cosine of 5 pi over 6, okay? And what will that give me? Okay, the sine of 5 pi over 6, which is over here, pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, and 6 pi over 6 would be pi, so we know we're on track. So this is 5 pi over 6. The sine of it is like the sine of 30 degrees, so it's like 1/2. So you're going to have 1/2 on the top. positive 1/2 because the projection on the y-axis here. Okay, and on the bottom is like the cosine of 5 pi over 6, which is like the cosine effectively of 30 degrees, and it's negative because it's going to be over here. Okay, and so what you're going to have here is negative square root of 3 over 2. Negative square root of 3 over 2, because the cosine of some multiple of 30 degrees is always going to give you square root of 3 over 2. It just depends on what quadrant you're in as to if it's going to be negative or not. It's negative because we're over here. The projection is going to be negative over here. Okay, so you can see right away the 2 will cancel with the 2. Okay, and so in the end what you'll have is 1 over square root of 3, and it is negative. Okay, it is negative. So the answer is 5 pi over 6, just like we said. The answer is 5 pi over 6. Now you always have to ask yourself, did it fall in the right range? Okay. Notice that for the cotangent function, which was the original function, if you look back before, for cotangent, the angles that you need to return was 0 to pi. Okay? And notice that this did fall between 0 and pi because here is 0 and here is pi. So this angle did fall where we were. Now what if you screwed up here? So we know this is the right answer because we got an angle, we plugged in here, and we got the right answer that we got, that we were asked to find up at the beginning here. Okay, but the thing you always have to ask yourself is, well, you know, everybody might not have come to the 5 pi over 6 to begin with. What if you picked a different angle? What if instead of 5 pi over 6, you know, just because you started at a different point, what if you chose negative pi over 6? Okay, what if you chose negative pi over 6? Well, your first instinct, without thinking about it, might have been to do that. If you take sine of pi over 6, well, let's just do it right here. Sine of negative pi over 6, okay, over cosine of negative pi over 6. What would you have done if you had done that? Well, negative pi over 6, here, the sine of it's going to give you negative, okay, so it's going to give you negative 1/2, okay, because you're projecting this guy over to the y-axis negative here, and it's going to be 1/2 because it's basically 30 degrees. Sine of 30 is always 1/2, okay, and for cosine, it's also taking the cosine of this, but the cosine is going to be positive because it's projecting over here on the x-axis. So that would be a positive square root of 3 over 2, okay, because cosine of 30 is square root of 3 over 2, and it's positive over in that quadrant. So you would have gotten the same answer, negative 1 over root 3. So what I'm trying to point out to you here is if you had started in a different place as I did, and if you would have gone and said, well, I'm going to try an angle of negative pi over 6, and I'm going to take the sine of it and the cosine of it, and I'm going to reduce it, and look at this, I got the right answer. Well, you see, that's not right, because you always have to look back at the beginning of the problem and realize that you were talking about a cotangent function, okay, and the cotangent function only can return angles between 0 and pi. Only between 0 and pi by definition. So this angle that you picked without thinking to begin with was negative pi over 6. And it worked, but it just isn't legal for what the inverse cotangent function can return, okay? Because you have to get an angle between 0 and pi. So what we're running into here with this little sub-example here is the multiplicity problem with all of these trig functions. There are multiple angles that you can get, that you can find, that you can legally put in and get the answer. But the inverse trig functions are only defined to return values in a specific range, okay? So when you're doing these inverse things and you're going around the unit circle and you're finding angles to satisfy them, you just have to make sure that you're picking angles in the range that you're supposed to. So when you're dealing with a cotangent and you're going to start picking angles and start plugging them in, you want to make sure you pick angles in the right range, which would be between 0 and pi, and don't start looking at negative. A different trig function, it might be perfectly okay to look at a negative. You just have to look at that particular range. Okay, so we started with cotangent, and we converted into sine and cosine, and I like to deal with sine over cosine, so I flip things over, and that's how we proceeded with that example. Okay, now the next question says, what if I'm taking the inverse sine of negative 1 over square root of 2? Okay, what this means, just like everything else, is it means that we're taking, and this is returning some angle theta, is we're taking the sine of some angle, and what we're getting back is negative 1 over square root of 2. So all we have to do is find this angle, but don't forget that because we're talking about the inverse trig function and we're talking about some angle we're getting back, the angle is going to be between negative pi over 2 and pi over 2. by definition. There's nothing magical, it's just the definition of it. So when you're picking your angles to see if it satisfies, you have to make sure you pick them between this range because we're talking about sine. Okay? So you have a unit circle here. Always helpful to draw that circle. It's kind of a crutch really more than anything else for me. Okay? So if I pick an angle of pi, let's say negative pi over 4, okay, which would be down here at negative 45 degrees here, what would happen? Well, the sine of negative pi divided by 4, okay, what was going to happen here? Well, at the sine of here, this is like negative 45 degrees. It's going to be for the projection along the x-axis, which is negative down here, so it's going to be negative square root of 2 over 2, okay? Negative square root of 2 over 2. Now that looks different than what we started out with, but I think you remember from one of the other problems, it really is exactly the same thing because I can take square root of 2 over 2 and I can multiply it by the fraction square root of 2 over square root of 2. I'm just proving to you that these are in fact the same thing. On the top you will have square root of 2 times square root of 2 is square root of 4. On the bottom you will have 2 times the square root of 2. Okay? On the top you'll have negative 2, root 4 is 2, and on the bottom you'll have 2 square root of 2, and these will cancel, so you'll just have the negative 1 over square root of 2. I'm just showing you that they're in fact the same thing. Okay? So if you pick negative pi over 4 for your angle, and you take the sine of it, you will get what you were supposed to get, which is negative 1 over root 2. And you have to always make sure the angle that you chose is in the angle range here. Okay, the next problem is going to be the arc tangent of negative square root of 3 over 3. And that's going to return some angle theta, okay, and we're trying to find out what that angle is. Now, the fact that this arctan is nothing fancy, it just means inverse tangent, same old thing. So what this means is the tangent of some angle is going to be negative square root of 3 over 3. That's what it means. And when you look at the tangent function and what the range of angles that it's legally able to return, we said that it's going to return, if you look back at the other thing, something between negative pi over 2 and pi over 2. Not inclusive, okay? Not inclusive of negative and positive pi over 2, but all the way up till that point, and that's because the tangent function has the singularities, those asymptotes there, okay? So all we have to do is find an angle, and we just start walking around the unit circle until we find an angle in this range that satisfies this. That's all we really have to do when we do these problems. Okay? So I like to draw a unit circle all of the time, just makes me feel better. And tangent, don't forget, is just the sine of theta over the cosine of theta. I always like to break up my tangents like this because it helps me find the answer. Negative square root of 3 over 3. So what happens if I pick an angle, let's say if theta is equal to negative pi over 6. Let's see what happens. Let's see what happens. Well, then I would have sine of negative pi over 6 over the cosine of negative pi over 6. Okay? And what would that do for me? Well, pi over 6 is like 30 degrees, and it's negative, so it's like negative 30 degrees. So that is where your angle is at negative pi divided by 6, roughly. That's roughly 30 degrees, okay? So the sine of this negative down here is also going to give you negative because that's projecting along the x-axis, and sine of 30 is 1/2, so it's going to be negative 1/2 on the top. And on the bottom, it's the cosine of the same angle. Cosine is going to give you a positive number because it's projecting along the x-axis, so it's positive, and cosine of 30 degrees is square root of 3 over 2, so it's square root of 3 over 2. Okay? That's going to give you that, and then this is going to cancel with this. The 2's are going to cancel because they're both in the denominator, so you're going to have negative 1 over square root of 3. Okay? And the first thing you should do is look and say, well, did this give me what I was trying to get? It doesn't look like it does, but if you just multiply top by square root of 3 and bottom by square root of 3, you will find the following. Okay? You're going to have, because you're multiplying by 1, so you haven't changed anything. You're just manipulating it. You're simplifying it. 1 times square root of 3 is square root of 3. And on the bottom, you're going to have square root of 3 times 3 is 9. Okay, and obviously the square root of that is 3. So you'll have negative square root of 3 over 3. Which is the answer here, and that matches exactly with this. So that actually isn't the answer. The answer is the angle that we chose, which is negative pi over 6. And you just want to make sure, just for sanity check, negative pi over 6 is between negative pi over 2 and positive pi over 2. This is negative pi over 2. This is positive pi over 2, so it is in that range. So all we did was we wrote it in terms of the function, used sine and cosine because that helps you walk around the circle and plug in values. We picked some angles. Well, I didn't pick more than one angle. I know what the answer is, but as you get comfortable with it, you'll start to figure out and see patterns in the multiple of the angle that you'll need. But even if you had no idea, you could just start with random angles there and just kind of walk around until you get an answer that gives you what that inverse tangent is, and you just have to make sure that that angle is in the range that you need. Okay, what if you were given a problem like the sine of the inverse sine of 0.7? What would that equal? Okay. Well, this is a little bit of a trick question because I'm taking the inverse sine of a number between positive and negative 1, and I'm going to get some angle from that, and I don't even need to calculate that angle, but what's going to happen is I'm going to take the angle that I get here and I'm going to immediately take the sine of it. So you see, I'm kind of canceling this sine with this inverse sine, and I'm going to get 0.7 as an answer. You can just sort of write that down because whatever this is, I'm going to take the inverse sine of it. I'm going to get an angle. I'm going to get an angle between positive and negative pi over 2 from our chart over there, okay, from our definition. And then I'm going to take whatever angle that is, and I'm going to turn around and take the sine of it. So I'm going to convert it right back into a number, and I'm going to get 0.7. That's kind of a no-brainer. You can write those down pretty quick. But what if I mix it up a little bit and I say, what if I have the cosine of the inverse sine of square root of 3 over 2. Okay? The cosine of the inverse sine. Well, it's just like anything else in life. You have to start small and go ahead and evaluate the inside, get the answer, and then evaluate the outside. Okay, so let's work with the inside first, the inverse sine of square root of 3 over 2. What that means is that the sine of some angle is equal to square root of 3 over 2. Okay? And I just need to find out what that angle is. And by the way, because we're talking about a sine, the angle, okay, the angle by definition must be between negative pi over 2 and positive pi over 2. I'm drilling this into you every problem because it's really important that you keep that in mind. So what angle is going to give me, so that I take the sine of it, it's going to give me the square root of 3 over 2. Well, I think you can convince yourself it's just going to be pi over 3. Okay, it's just going to be pi over 3 because this is like 60 degrees, and sine of 60 degrees is square root of 3 over 2. This angle does fall in this range, and that's what you would get if you put, this in a calculator. Inverse sine of square root of 3 over 2, you would get that angle because that falls in the range there. Okay, so then you just take that and you plug it in, cosine of pi over 3, because that's what the inside was. And cosine of pi over 3, again, if you just look at your unit circle, pi over 3 is like 60 degrees, so it's up here. This is, because this is 30 degrees and this is 60 degrees, so this is pi over 3 up here. Okay, so it's in the first quadrant. You're going to get a positive number because it projects down on the x-axis here. Okay, and that's going to be 1/2. Okay, that's going to be 1/2. So the answer to the problem is 1/2. So if you were to take the inverse sine of square root of 3 over 2 and then take the answer and then just take the cosine of it, you would get 1/2. Okay, because that's the what you would get when you project it on the x-axis there. And if this stuff isn't clear, I mean, we've done a lot of problems here with taking the inverse sine, inverse cosine, and walking around the unit circle. And you know, if you haven't done this stuff in a long time, it actually can be quite confusing, even if you've studied it before. You really need to think about reviewing that. A good way to do that is to pick up the Trig and Pre-Cal DVD. I've got several hours of just refresher on that stuff if you need it. One final problem. What if you take the arc sine of the sine of 5 pi over 4? Now, the first thing you might think is that the answer is going to be 5 pi over 4 because you're taking the arc sine of the sine. So you might think, well, these are just going to cancel like before. But this is a little bit trickier, and there's the reason why I did this problem is to show you the following. Let's work with the inside first. Okay? So what this is saying, what is the sine of 5 pi over 4? Okay, if you look at your unit circle, this is not an inverse sine. This is just a sine. This is a unit circle. This is pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. So this is actually 5 pi over 4 right here. down there. Okay, so what would the sign of that be? You know it's going to be square root of 2 over 2 because it's a multiple of pi over 4. Okay, that's something you should know from your trig. That's going to be square root of 2 over 2. But because it's down here in this quadrant, it's projecting on the negative y-axis there. So this is actually going to equal inside here negative square root of 2 over 2. Okay, because it's projecting down here, negative square root of 2 over 2. So now what you have to do is plug that in and say, okay, what's the arc sine of negative square root of 2 over 2? What would that be? So that would be the answer. That's going to give you some angle back, and since we're doing all this arc sine stuff, we're just going to rearrange this, and we're going to say the sine of some angle is going to give me negative square root of 2 over 2. Okay? All we got to do is find that angle. But don't forget, because we're talking about a sine function, the angle, just to drill it in, is going to be between negative pi over 2 and pi over 2, and that's just from our table at the beginning of the lesson here. Okay? So we have to find an angle in this range. That's all your calculator would ever return to you, and all a computer would ever return to you if you put this in there. Okay? So what would it be? What angle would it be? What angle is going to give us that? Well, forgetting about this 5 pi over 4 now, we just kind of get rid of this. Let's start with our unit circle. If we start with, and by the way, we know it's going to be a multiple of pi over 4 because we're getting a square root of 2 over 2 out. What if you go up here to pi over 4? Well, the sign of that is going to give you positive, okay? And what if you go to 2 pi over 4, 3 pi over 4 here? Well, that's going to give you a positive. Well, you see, you're already outside of the bounds. You can only pick angles from negative positive pi over 2 by definition. So let's go the other way. Let's go negative pi over 4. The answer is going to be negative pi over 4. Okay? Because if you look down here, this is negative pi over 4, and if I take the sine of that angle, it's going to give me a negative, because I'm projecting down here, negative square root of 2 over 2, which is what I want, and negative pi over 4 is in the range here. You see, there was another angle, you know, maybe over here, if you would have kept going over here, that would have satisfied it, but that's too far, because you can only pick angles between negative positive pi over 2, because you're dealing with the inverse sine. So, the reason I did this problem is because at first glance you might think arc sine of a sine of an angle is just they're going to kind of cancel and you're going to get this back. But because of the ranges in the angle that was chosen here, okay, really to boil it down, the reason it didn't work this way is because this angle 5 pi over 4 is down here, which is outside of the range of what an arc sine can return, which has to be between negative and positive pi over 2. So when you take the sine of it, you map this thing back over here, and then when you take the arc sine of that answer, it's going to basically map it over into one of these quadrants over here. So because of that, you're not going to get the same angle back. The moral of the story is when you're taking arc sine of a sine or sine of an arc sine or something, you just work with the middle and do it one step at a time. In this case, we took the sine of the angle, we made sure we got the right answer there, and then when we did the arc sine, we just made sure that the angle that was returned, that we picked, was inside of the range of angles that are legal for an arc sine. So in this section we cover quite a bit. Personally, I think this part of calculus is a little bit dry and confusing, but it's very important actually, because you deal with sine and cosine tangent and all these things all through calculus, all through engineering, all through physics, and they're really amazingly prevalent all through nature. So you're going to need to know them. When you start talking about the inverses, okay, you just need to be aware of what range of angles the inverses can return, because from the very beginning of the class I showed you that because these sine and cosine functions go on and on forever and repeat themselves, for a given input they can return many, many outputs. So in order to prevent that ambiguity from coming up in your math, you have to pick a range of angles that it's going to return kind of over one path here. And for each function, it's a little bit different. And that's just by convention, and that's just the way it is. You have to memorize them. And when you do your problems, you make sure that you honor those ranges when you find the angles that those inverse trig functions are returning.